Hi everybody, welcome to 3.3 Notes, take 3. That's right everybody, I've recorded this video 3 times because the first 2 times didn't work, mostly because I am not very smart and I did not turn on my microphone. So the first thing we're going to start talking about today is what is the inverse of a function. Well, as I mentioned yesterday, in function notation, typically I take a number x, I plug it into some other function called f, and what comes out is called f of x. An inverse function is when I take that f of x and I plug it into a different function called f inverse, which is denoted with a little -1 to the top right of f. What that would do is if I put f of x in there, I would get x back out. And as you can see, the function f and f inverse will undo each other. And it doesn't matter what order you do it in. You'll get the same number that you put in at the very beginning out as the ending result. In other words, f of g of x is x and g of f of x is x. Now this is important that when you see that -1 in the top right of the letter f, it does not mean the reciprocal of f, it means the inverse, okay? So these are not exponents. Okay? In algebra, you're taught to find inverse functions by switching x and y around and then solving for y. The graphs of inverse functions are symmetric to the line y equals x. Here's what I mean by that. Find the inverse function of y equals 3x plus 1 and graph both functions in the coordinate plane. Well, to find the inverse function of that, you switch x and y around and solve for y. And so in that case, I get x minus 1 equals 3y, or y is equal to 1/3 x minus 1/3. Let's graph both of these. I'll graph the original function in red, y equals 3x plus 1. Okay. And so I graph that line as best as I can. There it is. Now the other function I'm going to graph in green, the y equals 1/3 x minus 1/3. So minus 1/3 I have to estimate a little bit. And for every 3 I go over, I'm going to go up 1. So we have about right there at 2/3 maybe. And here's the function, the inverse. Okay, so if I called the original function f of x, the green function would be f inverse of x. And you can see, hopefully, that if I draw the line y equals x through this on the same coordinate plane, that the red line reflected over the blue line gets me the green line. That is, if I draw a perpendicular or normal line to this graph and keep going, I will intersect at the inverse point. Okay? Now, if I call this point A and this point B, A would be located at some x value. In this case, it's going to be at 1, 4. And notice where B is at. Okay? B is at something different. B is, well, actually, it should be, if I drew my line correctly, it should be at 4, 1. You can see I switched the x and the y around. Okay? And so I obviously can't draw a perpendicular line very well, but you kind of get the idea. That should be here. The inverse point would be switching the x and y around. Now, finding an inverse function this way is usually not assessed on the AP exam because it becomes very difficult to do this for all functions. In fact, in the next example that I'm going to skip, you would have to have the domain restriction that x is greater than or equal to 0 in order to have the inverse function. And we'll talk about that more in class. But for the sake of this video, let's focus on what the goal is. My goal of this, after reviewing what an inverse function is, is to find the derivative of an inverse function at a specific x value. And so the method that we're going to do today involves 5 steps, and it's listed out right here. And I'll let you read those if you want to pause and then come back. Let's go through those 5 steps. Use method 2 to find the derivative of f of x equals x cubed minus 4x squared plus 7x minus 1 at the x value of 1. Alright, so let's talk about the first step. The first step is to take the x and the y value and switch them around. So I'm going to go ahead and do that, but I'm not going to bother solving for the solving for the y value, because you're going to notice it's going to be pretty difficult to do that after I switch the x's and the y's around. So you can see here, this is what the function becomes after I switch x and y around. Step 2 then is to take the derivative of this implicitly with respect to x. So I have 1 equals 3y squared dy dx. Remember that since I'm taking the derivative with respect to x, I have to do that dy dx every time I take the derivative of a y term. So I have 8y dy dx. minus, or plus rather, 7 dy dx, even on the one where you have a constant. And then the derivative of negative 1 is going to be 0 dy dx, but I don't need that. So in this case, in the third step then, would solve for this, for dy dx. Dy dx would equal 1 over 3y squared minus 8y plus 7. And I did that by factoring out the dy dx in every term and then dividing both sides of the equation by the coefficients 3y squared and negative 8y plus 7. All right, step 4 then is to take the function from part 1 that after I switch for x and y. I'm going to take this expression here and I'm going to plug in my x value to find what y would have to be to make this true. So the x value is 1, so I'm going to plug 1 in for x, and I would use a calculator to solve this. Now to use a calculator to solve this, what I would have to do is make one side of this equation equal to 0. So it would be 0y equals y cubed minus 4y squared plus 7y minus 2, and I'd use the solving feature of my graphing calculator. Now by doing that, I did that off screen beforehand several times, because like I said, I've tried to record this video a few times now. It would be 0.3494, or just 0.349. Now I take this y value, again remember I solved for y here, and plug that into this derivative function, and that's my final step. Is I'm going to have 1 over 3 times 0.349 squared minus 8 times 0.349 plus 7. And using my calculator, that ends up being roughly 0.219 if I round. You could have 0.218 if you did not round. Let's find the derivative of the inverse function using the same method for this function when x equals 3. Step 1, switch x and y around. Originally it's y equals e to the x plus the natural log of x. If I switch that around, I get x equals e to the y plus the natural log of y. Okay, again, you could always pause. I know I'm going pretty quickly through this. Then I take the derivative with respect to x, and I get e to the y dy dx plus 1 over y dy dx. Then in step 3, I solve for the dy dx, and I'm going to factor out, I'll show all my steps this time. I factor out the dy dx, I get e to the y plus 1 over y. Then I'll divide both sides of the equation by e to the y plus 1 over y. And I, of course, use the symmetric property to switch these two parts around as well to put dy dx on the left. In step 4, I'm going to take this original equation after I switched it for x and y, and I want to use the x value, and the x value is 3, so I let 3 equal e to the y plus the natural log of y. Subtract 3 from both sides and use a graphing calculator to find where this graph intersects the x-axis, and then y would be approximately, in this problem, 1.074. Finally, in step 5, we take the derivative expression 1 over e to the y and plug in the 1.074 in for y and use a calculator to evaluate, and I get 0.259. So those are our 5 steps, which can be summarized in the following formula. To find the derivative of the inverse, f inverse prime, that's how I write it. I put a parentheses around f inverse. I use the prime notation of x is 1 over f prime of f inverse of x. Okay, so I want to point out why this formula works. If you've noticed in the last 2 examples, really, I'm just taking the derivative of this function, right, and putting in the denominator of this expression, right? And instead of having x's, I have y's. All right, can you hopefully see that? Let's look at the other one. Remember how I had this long polynomial, cubic polynomial here? If I took the derivative of that, I'd get 3x squared minus 8x plus 7, which is what goes in the denominator here, except I use y's instead of x's. And so this formula is summarizing that whole process, is that instead of having f prime of x in the denominator, it's actually f prime of y. Okay? So that's a y value that we're using as f inverse of x. Okay? So let's find the derivative of this function, x plus sine of x, when x equals pi. Okay, so we're going to use this formula, f inverse prime of x is equal to 1 over f prime of the y value. Okay? Now what I need to do then is I'm going to let this x value become the y value of this function. Pi equals x plus sine of x. And to solve that for x, I would move this to the other side by subtracting pi. So move the pi to the other side, and then use a graphing calculator, or if you know your trig functions pretty well, you should know that if I plug in pi, it's going to work, because I'll have pi plus 0 minus pi. So then that value of x goes in here. So I have 1 over f prime of pi, which is weird because it actually turned out to be the same x value here that we had, but it is different. I'll show you in the next example. And so then I take the derivative of f. What is f prime of x? Well, it would be 1 plus cosine of x. This would be 1 plus cosine of pi in the denominator, which is 1 over 1 plus negative 1, which means that the derivative of the inverse is undefined at x equals pi. Because 1 plus negative 1 would be 0. I get 1 over 0. All right, let's do another example. Find the derivative of the inverse of the function f of x equals 1/4 x cubed plus x minus 1 at x equals 3. And so again, we're going to use that formula. F inverse prime when x equals 3 is going to be 1 over f prime of f inverse of 3. Now remember that this here is going to be the y value. When y equals 3, what is x? That's really what I want to know. Because on the original function, I would have something, comma 3, and on the inverse, it'd be 3, comma something. So these two numbers would be the same. So I want to know what is x when y equals whatever's inside of here. So when y is 3, what is x? So I set 3 equal to y, and I want to find out what x is. Now you can either use guessing and checking with like integer values, or you could do what I do and use a graphing calculator. There are methods to solve cubic equations for x, but in this case, don't spend too much of your time doing that. Use a graphing calculator to find out that x would have to be equal to. Then, let's find the derivative of this function f. F prime of x would equal 3/4 x squared plus 1. Because then, when I use this formula, it would be 1 over f prime of 2, because 2 is what value of x got me 3. So I have 1 over and 3/4 times 2 squared plus 1, 1 over 3 plus 1, 1 over 4. Now, of course, I'm going at a breakneck speed here. I want to just point out that I just took the derivative of f, put in the denominator, and plugged in the 2 that I got from setting the original equation equal to 3. So I set the original equation equal to 3. I solve for x. I put that inside of the derivative of f, and then put that in the denominator, and that's how I got my answer. We'll do 2 more examples, and then we'll be done here. Let's say we have a strictly monotonic function. We haven't talked about monotonicity in this class, but that basically means it's always increasing or decreasing. We don't know which one it is. We can look at the table and figure out pretty quickly that if the y value is going from 5 to 1 to 0 to negative 3, this is going to be always decreasing. And the reason that they say if it's monotonic, monotonicity typically implies that there is a inverse function at all x values. Okay, and so if I want to find g inverse prime of 1, g inverse prime of 1 would be equal to 1 over g prime of g inverse of 1. Now again, let's talk about this g inverse of 1. Well, g inverse of 1, if I put 1 into the inverse, I would get the x value that went into the original function. So if this is f inverse of 1, if this is f inverse here, right, or g inverse rather, because it's g, then on the original function g, it would be x1. So I want to know what value of x gets me a g value of 1 in the table. So if I look at the table, when is g 1? G is 1 when x is negative 1. So that's why I put negative 1 in to this expression g prime of x, because that's the y value that gets me negative 1. So 1 over g prime of negative 1, g prime of negative 1 is negative 1/5. So my answer is negative 5. If I want g inverse prime of negative 3, I do 1 over g prime of g inverse of 3. And again, I'm asking myself, what value of g would get me 3 as the output? Okay, right? This is the inverse, and here's the original point. What value of x gets me 3 in g? Well, actually, negative 3. I can't read. I keep doing that. I did that the first time I did this problem. What value of x gets negative 3 for g? And it's 4. So 1 over g prime of 4, 1 over negative 2. G prime of 4 is negative 2. Okay, so there you have it. Like I said, this is a challenging lesson. We'll go over this in great detail on Friday. If this was too fast for you and you want to just see somebody else work on this, one of my colleagues, Tony Record, he's a great mentor of mine in calculus. He's a teacher in Indiana. He's really great at this. I've based a lot of my notes off of his materials. If you scan this QR code, you can watch Mr. Record do another problem, or these examples rather, and that should help you if you needed some more practice on this. Thank you for watching. If you are stuck, make sure to watch the live class video on Friday when you have time, and we'll talk to you soon.